Hello, everyone. My name is Charles Chen. I'm currently working at Intel as a cloud software development engineer, and I will be the moderator of this session. The topic of this talk is network programmability squared. This is my pleasure to introduce our speaker, Satoru Matsushima, and Satoru is a technical master at Softbank. In today's presentation, he will explain the network programming model for SRv6 mobile user plan and the benefit of this model brings to the network architecture and operation. He'll also describe the challenge that SoftBank faced in the first operator leveraging SRv6 and P4 to build the mobile user plan for 5G and how they overcome the challenges collaboratively. So Satoru, please take it away.
Thank you, Chan. My name is Satoru Matsushima from Softbank. Today I'm presented network programmability squared on behalf of my co-authors, Ahmed, Pablo from Cisco, and Tetsuya and Chava and Kariani and Keiyu from Arcus, and Katsuhiro and Ashik and Yuya from Softbank. So let's start. Oh, just to begin with much detail with my slide, that the slide shows the SRv6 network programming model for SRv6 mobile user plan, as Charles explained. I can remember that the almost 3 or 4 years back, in the IETF hackathon, IETF 105 or 104, our hackathon member implements some idea of the network programming, like a GTP to SRv6 status translation and vice versa. So you can see the slide on right-hand side. So this is a very rough handwritten sketch to share my hackathon member, so how GTP SRv6 translation works. So a GTP packet coming in, and some node translates the packet to SRv6 without a GTP header, and vice versa. The gateway receives the SRv6 packet, and then the packet translated to the GTP. That's really funny idea because just for the GTP packet as it is, what's the problem? But we have some interesting idea to process the GTP packet much easier. Then we found SRv6 programmability and come up with the idea for this translation. But basically, protocol translation much tend to introduce the problem to the network, because much of this internal state introduced in the middle of the network. To avoid that, but we found that idea is stateless translation. How statelessness be kept in the middle of the network is like this. So once the node receives the GTP packet as this packet header, then the node put that header information to IPv6 addresses, like this. IPv4 destination address, GTP packet, embedded in the middle of the IPv6 address here. And the other key identifier of the GTP packet is TID. So TID is also embedded in the middle of the IPv6 packet, IPv6 address. The rest of the header information be kept, as you can see here, IPv4 SA or QFI, RQI, very 5G specific IDs. very short length, but we can put into this place. That's what we figure out. The statelessness can be kept in the network, not to introduce the much more fragile state. So the basic use case at that time was just translate GTP and SRv6 and back to the GTP, because the 5G node only process a GTP packet, no idea to process SRv6 at that time. Then, but we found some network programmability beauty in SRv6. Then in the other network function implemented during the SRv6 path. That's what we imagined on the 3 years ago. So we define the detail of the processing of the GTP SRv6 translation in the internet routes. So you can see the pseudocode on left-hand side. It's a bit detailed, but the code, what the code does is really simple. So the once node receives the packet, keep the this is the SRv6 to GTP case. The GTP header be constructed from the IPv6 header and others. The node extracts the destination IPv4 address from the IPv6 address, and the other rest of the key identifier like a TID and QFI also extracted from this field. We called argmob session in the manner of the SRv6 network programmability. So the specification already matured. My friend and the colleague were implemented on both of the P4 code and BPP code as a software router. So this is what we had done before to utilize this function in the field of the our network. This is very fun in terms of the network programmability on both of the P4 and SRv6. So we really enjoyed. So after that, many people concerned that translation functionality in terms of the performance. When we mention that performance, it will be throughput, and other thing would be latency. So we measured this performance with the P4 implementation over ASIC, like Tofino. This will be, you can see the scientific paper accepted in the international conference in 2019. My co-author and I write up this paper with the measured performance in throughput on and latency on, you can see right on the right-hand side. In throughput, you can see the SRv6 translation function performance here, this line. You can compare the performance throughput to other network processing, like function of the GTPU, NCAP, DCAP, SRv6, NCAP, DCAP as well. Not much difference, rather than moreover, the throughput would be a little bit better than GTP, DCAP, and NCAP. That's the very powerful point of the P4, which very new network processing idea be achieved in the hardware acceleration with no performance compromise. You can see the latency as well. At that time, we need to keep the some confidential things. So just show the a normalized latency at the percentage. All of the GTP SRv6 and SRv6 GTP translation function be compared against the very basic layer 3 forwarding. So the SRv6 GTP translation performance in latency bit increase, but if you can see the SRv6 and GTP decap, the performance is not so much bad, and moreover, it will be negligible in the operational point of view. That's what we achieved from this scientific work. I really appreciate my co-author, Chengan and Kentaro and Hitoshi and Mie. You can find this paper from the URL in the bottom of the slide. Please take a look if you're interested. So now, the 5G, we are mobile network operator. So not only for us, but many of the MNO in the world are now building up their 5G network. But our 5G network are not only for us be built like this. You can see that this slide. So we built S3 network on left-hand side to aggregate the connectivity with the G node B for the our 5G client. On right-hand side, we built N6 network to connect to DN. DN usually the internet connectivity or other enterprise VPN or something. In the middle of the N3 and N6, UPF exists, controlled by 5G core functionality like IMF and SMF. UPF cross-connect the session from the terminal we call UE, user equipment. So the connectivity be handled at the UPF and then connected to the internet and other enterprise-specific network through N6 and DN. That's the really typical view of the standard architecture point of view. I think no one have doubt. What we are doing is like this, not only for us, or, but every 5G MNOs. So, but the reality is, especially for a network operator who adopt segment routing, the network operator built N3 and N6 network like this. So in some MNO case, the operator built up the one segment routing network for 5G. Not only for 5G, but also services maybe. over the segment routing network, the operator configure the buf for N3 side and also the N6 side as well. So N3 buf connected to G node B side and the UPF side import and exchange their route to consist of N3 VPN. On N3 side, the buf on DN side and UPF side extend the route to consist of N6 VPN. That's actually the operator who adopt a segment routing as an underlying network doing. That's really reasonable because there's no reason to build up the N3 network and N6 network individually because we have a very capable network segment routing to support the multi-tenant network to support the N3 and N6 connectivity to the 5G by one network. Very easy to understand, the much easier than build up two network. So this is a very reasonable way. Okay, in that network building, the packet path, packet flow would be like this. So as I mentioned before, all of the traffic for 5G goes through the UPF. In that architecture, the packet path flowing from UE and GNOB to UPF through N6 bar. And then the traffic back to the segment routing network with a GTP header into N6 bar, and then go out to the DN from N6 DN bar. This is very unfortunate because the it's obviously not optimal. So even the packet go into the segment routing network, that segment routing network hosts the N6 network as well. So, but the packet should go out once and then go in again. So not only for me, but many people imagine, what if we could do this? Like the packet come into the segment routing network in some buf for the N6, N3, whatever. Then the packet just go out to the destination in case this is the DN. What if we can do this? If we can do this, we can achieve the not only for optimized path like this, but we can also save the cost to support the huge traffic goes to the UPF. In that view, we just need to prepare enough bandwidth in the interface of on this and this. But if we cannot do this, we have to prepare the same bandwidth in addition to the N3 bar and 6 bars. We need to prepare the bandwidth on the UPF side on both of the N3 and N6. That's a huge cost saving opportunity for us. Not to mention the not huge traffic be supported through the UPF. To achieve this optimized path and cost saving, we found that the network programmability squared in that place. But if we successfully implemented in the network with the GTP SRv6 data translation, we can achieve that optimized packet path. When we introduce the this function in this place, the optimal data path be supported from the other side of the network. Here, N6DN buf side connected to DN. Basically, the packet from the internet come in to this interface, but without SRv6 GTP translation, the SR segment routing network need to forward the packet to here. The key is how to find the right destination to utilize this GTP service translation function from here. This is very big issue in the past. Even the many of the local breakout idea came up, but without this technology, almost all of the solution in the past be abandoned. So this is not an easy question, but we need to find answer. So we finally figure out we need architecture to enable to do that. So I and my co-author work together to find the right architecture to enable the best path, as I mentioned in the previous slide. This is the architecture of SRv6 mobile user plane architecture for distributed mobility management. So we call it SRv6 MUP or SRv6 map. We propose this architecture to IETF already. You can find the this architecture draft from the URL in the bottom of the slide. Please take a look. It should be fun, I believe. So let's look at the architecture very briefly using this slide. So we have almost two components defined in this architecture. We defined map C, map controller, to take the information from 5G core on the P router on both sides of the access side on the DN side. In the middle of the PE router, SRv6 transport network exists. You can see that each of the load of the node. The map C transform 5G core session to IP route, which is a really interesting work because the 5G handles the all of the connectivity by a session. So the map controller transform those sessions to IP routing information, which is really a different concept from the session base. But segment routing enables session to be transformed to the routing, which is a really interesting point. On the left-hand side, the P, this side translates GTP SRv6 in stateless, as I mentioned before. On right-hand side, PE, this PE routes packet based on the route from map controller. So this is a key to enable the stateless translation between GTP and SRv6 in network. As I mentioned in previous slide, find the function of the translation in the opposite side of the network be hard, but map controller inform that functionality and where it's running to the PE. So that's enabled to utilize the GTP SRv6 stateless translation in motion. So through this architecture work, we found another required work. So it is control plane protocol. So we found that the map controller can inform the session information be translated to routing information to the P router, but how to inform that session as a routing information? It requires control plane protocol extension. So we need to work on that. After some discussion with my cursor, we come up with the BGP extension to support such session to routing transformation. The BGP is a container to bring that routing information from the map controller to PE router. It's not require much extension. It requires just one SAFI, one of the key BGP parameter of the address family. Just one additional server's address family identifier with the route type. The protocol extension should be kept in minimum. Otherwise, much of the coding and the fragile control plane be introduced. But we successfully introduced the lightweight control plane utilizing existing BGP mechanism as much as possible. Oh, you can find the this document from the URL on the bottom of the slide. Please take a look. So we enabled to do that, but it's not just the packet path between the GNB and DN, but also the MEC server, as you can see here. The PE router is just normal BGP router. It means that the MEC server itself could be a PE router because the many of the software BGP implementation are available for the server implementation. So once the that extension implemented in the software BGP router, MEC server itself be a PE router, and then the packet from the application to the UE device directly forwarded to the SRv6 network toward the UE device. That's the another benefit of the SRv6 MUP, SRv6 map by transforming session information to routing information. So you can see this picture, what if we couldn't implement SOP6 map? Without SOP6 map, the operator needs to establish additional network. It's called N9 network and N6 network. Of course, those networks can be built as a VPN over a segment routing network, but all the traffic still need to go through the UPF. In addition to the one UPF, but also the other UPF is required to handle the traffic toward whether the internet or for MEC. That's other the benefit of the SOP6 map to avoid such an overhead of the service as 5G network construction and operation. So we explain the architecture work and the control plane protocol work to utilize data plane programmability using P4 and SRv6. Not yet to mention the data path function itself. So let me explain a little bit. I have to confess, I'm not a P4 expert, but I experienced much good implementation work with my co-author, especially for the P4 programming to how to save the number of pipeline stage and table size and other critical parameter like PHP. Through that implementation work, we found that the very important takeaway, in addition to the operator usually taking care. The operator basically interested in how many routing entry be available for the hardware coding engine, because the hardware resources is really limited. So how many entry be supported is always concern of the operator, because the internet route keeps increasing, and also our number of customer hopefully increasing with the good revenue, but many people know that the just increasing the number of the device and the line without the revenue increasing. So that's the hard situation for all of the operator. So usually we care about the field resource. But in addition to that, once operator come up with their idea to utilize the programmability of the hardware using P4 or SRv6 network programmability, we need to care about the another resource of the hardware, such as number of pipeline stages. It's of course depends on the how complicated the network function be implemented. But in our case, SRv6 map require a certain number of the pipeline. So we need to save the pipeline consumed. That's a really interesting work, but not easy. So that's a really good experience for me. And of course, there are table size on each stage. Basically, the ASIC has very limited resource of the memory. We need to be careful. And other things is PHP. PHP is a packet header vector, which is a very interesting issue there, because the SRv6 map leverage the very flexible routing the mechanism, such as longest match with the embedded parameter inside of the IPv6 network, which consumes the many PHP resource. So we need to find a solution to how to save that resource and how to the implementation be flexible to keep the network operation flexibility. That's the brief introduction of the P4 experience, but not the main contents in this presentation. But I'm hope we can have another chance to explain the much detail of the that challenge in the future. So let me explain very briefly. So why we really eager to do that novel network programmability be introduced in our network. This is because our future networking require much scalable and stable operation with much lower cost. Today, as is, we just provide internet connectivity through the Anchor UPF for the mobile devices right now. But not only for us, but many people see the opportunity when the 5G available widely. Many use cases for not for smartphone with the broadband service, but also the other use case like autonomous driving or IoT or something. But based on the basic architecture, we need to support a bunch of the session for a bunch of the next side. It introduces a much session-heavy operation, which increase the very critical point of the network. It to be the session-oriented operation tend to be fragile, so we want to avoid that operation be happen in our network in the future. So what we want to do this with the SRv6 map is like this. In the middle of the path, the SRv6 network supports the those session path as a route. So the difference between session and route is the one-to-one vs and one-to-many. That reduces the big risk of the session handling. Instead of that, the routing information spread out to the underlying network. To introduce not just best optimal path, but also the much stable operation with much cost saving to support the future use case. There's no big difference for the future we can see, but the performance and cost-wise, there's a big difference there. But nobody see right now. But what we did in the past, as you can see, internet replaced all of the telco-oriented infrastructure like telephone exchange switch, ATM switch. Those old session-based circuit switching technology be gone. Instead of after that, internet bring the technology based on the routing. So we again do rise that things to the 5G with SRv6 map. That we are trying to do. So let's introduce the demo movie of the SRv6 map. We did in the MWC this year. Not a full video, but it would be good to show the packet path compared to the SRv6 map, to the, not the SRv6 map enabled. Let's play this. You can see right-hand side and left-hand side. On left-hand side, the packet goes through the UPF on the bottom of the picture. But on the right-hand side, you can see the packet as a green rectangle directly goes through the next side from the UE side. You can find the this demo full video in the Intel site of the MWC page. Please take a look if you are interested. So this is a brief summary of my presentation. So SRv6 and the P4 squared network programmability enables mobile operator can get a chance to evolve 5G mobile user plane. As a takeaway, network architecture work and control plane protocol work will be required to fully leverage the programmability of the data plane. Operators need to be aware which ASIC resources available and how much consumed and remain. So I'm happy to share this summary of the takeaway. Thank you very much. I really acknowledge for Chengan Lee and Kentaro Ebisawa and Hiroshi Kuwata and Miyako. Oh, this is a very much trivial FAQ. Many people ask the so SRv6 supports the SRv6 map, but what about SRMPS? SRMPS can support the MUP. The answer is SRv6 map is application of IPv6, so SRv6 map can run over any IPv6 VPN solution, not only over SRMPS but also legacy MPS. Thank you very much. That's all my presentation. I'd like to hand off to the Charles.
All right, thank you for the great presentation. I got a few questions. So the first one is that in your first slides, you show this like the packet header of transforming the GTP packet into
Right.
SRv6. One thing I noticed there is that you keep the tunnel endpoint ID, the TID in SRv6, meaning that you're not actually terminating the GTP tunnel. You still keep that tunnel ID. You just use a different header for it. So I'm just curious, compared to the solution where you terminate the GTP tunnel at the P4 switch and just make it a pure IP packet, what's the benefit of using SRv6 here? And what's the benefit of keeping that TEID in the packet header? Can you give an example of such use case?
Okay. This is the actual use case we are trying to do here. Of course, you're right. The GTP packet easily terminated in this point. There's no reason, maybe, to translate the packet to SRv6, but to forward the inner packet capsulated in the GTP header, we need a routing table to find the right forwarding destination for the inner packet. In that case, we need some sort of the forwarding mechanism to the right place to look up the inner packet to route the packet. If the
I see.
N6 buff exists on same node, so both of the N3 RAM buff and N6 DN buff exist in same node, there's no reason to translate the GTP packet to SRv6. It's obvious. But on other direction, packet goes in, come into the N6 buff from DN without GTP packet, without GTP header. Usually, the packet forwarded to the another buff on the UPF side, like this. But what we are doing is like this path, okay? But if the packet arrived at this point from that point, how to find the right identifier for the packet to gene B? This gene B doesn't understand the SRv6, so we have to reconstruct GTP header to make this gene B available to forward the packet to this device. In that case, we need a TID in the IPv6 address. Okay, so a packet goes in, come into this point, and this buff finds a route to forward the packet to here. Okay, but this point need to reconstruct GTP header with right identifier. Okay, so then this node requires TID. Then this buff put the TID informed from the map controller to the IPv6 in the middle of the IPv6 address. The packet forwarded to this node with the SRv6 ID. Then this node finds the TID in the SRv6 ID. And then reconstruct the GTP header with the embedded TID from the SRv6 ID. That's a mechanism. That's a use case of the utilizing SRv6 for GTP interworking.
I see. So I guess if your N3, N6 are in the same node or network, you probably don't need the TID, but you're thinking about a more complicated network in between. So you need to retain that TID across the entire network. So for the downlink direction, you can use that information to encap the packet again. Okay,
exactly.
I think
yes.
Yeah. All right.
This picture is really simplified, too much simplified, but in the middle of the path, we have usually a bunch of the
Yeah, got it.
node existed.
Okay. Just another quick question. You also mentioned in a conclusion that now the operator need to be aware of the ASIC resource allocation, right?
Right.
So I'm curious, what P4 target do you use to implement this work? Is that a Tofino switch, or is there some other P4 target? And if it's a Tofino switch, can you give an estimation on how large this system can be scaled in terms of maybe a number of UE sessions?
Okay. My previous work is based on the Tofino because there's only one device available in front of us. So that's a reality. No question that Tofino was our target device. But in the future, I think we have another option. Maybe my colleague from Cisco already prepared and shipped the hardware chipset to support the P4 coding. I hope we can utilize as soon as possible. And another question you mentioned was the scalability, our available resource in the hardware chipset. Actually, I don't worry much about the scalability in terms of the field-related resource, like longest prefix match entry or SRAM or some TCAM or something, because the existing device already supports the enough number compared to the bandwidth. The operator maybe typically calculates the required number of the entry based on the per subscriber bandwidth. The maybe 1 megabps or 10 megabps required for each of the customers. So then we simply calculate that total required bandwidth for the switch. So if the 100 entry required, 100 entry available, it means that the 100 meg in total required for that box. So it's a really easy math and easy target for hardware, but we typically see the several terabps bandwidth. We can see. In that case, we need to have a medium the route, medium the field entry be required. But it's also the question of the TCO. So if the hardware switch provided by very certain level of the cost, it'll be okay, because the even the device available for tens of thousand terabit BPS available with the much lower cost compared to the legacy device, we can accept the much less number of the entry of the forwarding. That's what we are calculating.
I see.
So,
yeah, that makes a lot of sense.
Yeah.
Okay.
In that our experience, we found the another resource be taken care of. That was the pipeline, number of pipeline and table size on each stage. So that affects the flexibility of the network programming. That's what we found the in the future we operator need to be taken care of.
I see. All right, that's all the question I have. Thank you very much again for your presentation. And I think that's it. Thank you.
Thank you.